Good morning, everyone. Today, we are going to present our project Mousetrap Card Challenge. Our team member are Arun, Regmi, myself, and my friend Bikas Pandit. In this project, we built a mousetrap power card and tested how it moves using the idea from the engineering dynamic. Introduction. This project is mainly about changing spring energy into the forward motion. We designed and built a small car using a simple material from the lab. The car was powered by only mousetrap spring. Though this project, we try to understand how force, motion, energy works together in a real moving car. Our focus was to make the car travel as far as possible when reducing friction and keeping the movement stable. Project Aim. The main aim of our project was to design and test an efficient mousetrap car. We want the car travel a good distance using only the energy stored in the spring. So we look at how the energy was transferred from the spring to the wheel. We also use our test to understand the car acceleration, velocity, range, and energy performance. 3. The main challenge was that the card had only limited energy. The only energy source was the mousetrap spring, so we had to use that energy carefully. If the spring released the energy too quickly, the card could move fast at the first start, but it might not travel very far. So our design had to balance driving force, distance, friction loss, stability, and wheel alignment. Let's talk about key components. The main parts of our cart were the mousetrap spring, lever arm, axle, and wheels. The mousetrap spring stores the elastic energy. The lever arm helps to release the energy more slowly and increase the travel distance. The axle transfers the motion, and the wheels change that rotation into forward motion. So all these parts work together to move the car forward. The next slide is about working principle. The working principle is quite simple. At first, the spring stores elastic energy when the mousetrap is released. The lever arm moves and pulls the string. Then the axle starts rotating and the wheels also rotate. Because of this, the cart moves forward. So, in simple words, the cart changes potential energy into kinetic energy. My friend, because now let's move forward. Experimental method. For testing, we measure the distance traveled by the car and the time taken. We look at the two parts of the motion. The first part was acceleration when the string was still pulling the axle. The second part was the deceleration when the string has already released and the car started slowing down. We did the three trials and used the stopwatch and measuring tape to collect the data. Motion analysis. From our test, the maximum velocity of the car was about 1.75 meter per second. The average acceleration was about 0.329 meter per second square, and the deceleration was about negative 0.089 meter per second square. The total distance traveled was 9.63 meters. This showed that car first gained the speed when the spring energy was transferred and then slowed down because of the friction and other resistance. Rolling resistance. Rolling resistance was one of the losses in our car. This happened because the wheels were touching the floor and there was also some friction around the axle and wheel. The rolling resistance force was about 0.01 newtons. It looked like a small value, but the small car with limited spring energy, even small friction can affect the final distance. Next slide is about aerodynamic drag. Aerodynamic drag means air resistance. When the cart moves forward, air pushes against it slightly. In our case, the drag force was very small, about 1.4 into 10 to the power minus 4 newtons. So drag was not the main problem of our cart, but we still included it because it's part of the real motion. It also makes the analysis more complete. The next slide is about drive force analysis. The drive force came from the mousetrap spring. When the spring was released, it created torque through the lever arm.
that pulled the string, rotated the axle, and turned the wheels. The drag force was calculated as about 0.054 newtons. We used Newton's second law to relate this force to the acceleration of the cart. This helped us understand why the cart moved faster at the start and then slowed down later. Next slide is about energy analysis. For the energy analysis, we compared the spring energy into the kinetic energy of the car. The potential energy stored in the spring was about 0.204 joules and the kinetic energy was about 0.20 joules. This means most of the spring energy was changed into the motion, but in the real test, some energy was still lost due to friction, drag, axle resistance, wheel rotation, and misalignment.
And discussion. Overall, our experimental values were close to the theoretical values. The car moved forward in a stable way and traveled a good distance, but the result also show that resistance reduced the acceleration and affect the total range. Well, inertia also had an effect because some energy was needed to rotate the wheel. So the performance of the car depend on both energy transfer and how much energy was lost.
The next slide is about the improvements. There are a few things we could improve in our design. We could reduce the wheel mass so less energy is needed to rotate the wheels. We could also improve the wheel alignment so the cart travels straighter. The another improvement would be reducing axle friction because that would help the cart move more freely. We could also make the shape slightly cleaner and repeat more trials to get the accurate results.
All right, let's come to the conclusion. Our mousetrap car successfully changed spring energy into the forward motion. This project helped us apply engineering dynamics like force, motion, torque, energy transfer, rolling resistance, and drag. These results show that the theory matched the experiment reasonably well, but real losses still affect the performance. For future improvement, we should mainly focus on reducing friction, improving alignment, and optimizing the lever arm and string system. Thank you very much for listening us today. Have a good day.